Geometry, geometry, that's the class for me. All right, 1-3, we're back. Let's do this. What's happening now? We are measuring segments. In the previous section, we saw that we could work with points like point A. We might come across segments like A, B. We might come across lines that go a little bit further, containing 2 points at least, like CD. We also saw rays. And so what's happening here? We're now measuring some of these segments using some numbers, which I think is really great. We will be thinking of these in one dimension, which is pretty nice, just from left to right versus up and down, to find distance between 2 points on a number line. We'll see this segment addition postulate and how we can combine segments that add together, creating a bigger distance, using a little bit of algebra in there. You still remember that, right? We will take a look at what it means for two segments to be congruent using this new symbol here. This is a fun one to draw. Find the midpoint of two numbers on a number line. Using a number line, you've been working on that since kindergarten. You remember that thing, right? Went around the room and looked like this. Had all the great numbers out there. Probably started at 0, then 1, then 2. So we'll be taking a look at that. Even a kindergartner could do this. Find and solve algebraic equations involving distance and midpoints. Those are good ones. This little clock puzzle gets you kind of in tune to how some of this will work. If a clock takes 3 seconds to chime 3 o'clock, ideally, how long does it take to chime 6 o'clock? Well, if you think of when a clock goes off at 3, there's the bam, 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 for every hour that's passed. So there's 1, 2, 3, that makes sense. So ideally at 6 o'clock, there should be 6. But we'll see that this might not be the case eventually. So just hold on to that thought. The ruler postulate says that every point on a line can be paired with a real number. This makes sense. This makes a one-to-one correspondence between the points on the line and the real numbers. The real number that corresponds to a point is called the coordinate of a point. So now when we're thinking of the number line, we'll be thinking of those points as coordinates, and we'll be thinking of them also as points. The ruler postulate allows us to measure lengths of segments given a given unit and define distance between 2 points on a number line. So we would be able to say the distance from A to B is the absolute value of A minus B. So recall that absolute value measures the distance between some number and 0. So we always want this to be a positive number. So anytime we measure distance, it's always positive. Hence why we're using absolute value. You wouldn't want to say that you're negative 4 feet 10 inches. That seems weird to say you're a negative height. So we want to make sure that distance is positive. Starting first with the number line. So we're trying to find SU. So we'll see 2 ways we can approach this with the algebra and absolute value, but also just from the visual. So I know that S is at -4. So here's my S value. I'm deducting the second value. The second value, what's the value for U? The coordinate for U on this number line right here. It's 10. It's right there. All right, algebra skills, let's see them. So -4 minus 10. I know that we're going more negative, so that's -14. The absolute value of -14 is positive 14. So the distance between S and U is 4 units. And so notice that when we talk about the length of a segment, we do not include the line above it. So we can just say that S to U is going to be 14 units. We could have also just hopped along this number line here and just counted up, all right, from -4 to 2, that's 2 units, 4, 6, 8, 10, 12, 14. That's another way. There's the right way, there's the wrong way, and then there's your way. So pick which one you think makes sense. Segment addition allows us to take segments with different endpoints and just add them together. This is saying that if we had the segment from A to B and we added on B to C, so from here to here, that would be rewritten as A to C because now we have two endpoints, one A, one C. Using this with algebra, in the diagram, J to L is 120. What are JK and KL going to be? They give us a little bit of information with the algebra here. So we know that from the beginning, J to L is going to be $1.20, 120. We also know that J to K is this, K to L is that. All right, so let's write this out. I know that J to L is equal to the sum of J to K. And what other segment? K to L. Yep. So what do we know? We know J to K could be 4x plus 6. We know that K to L is 7x plus 15. And we also know that J to L is $1.20. So recall some algebra. What can we combine here? Definitely the 7x and the 4x, getting us 11x. 6 and 15 gets us 21. So much fun. We can then take this further. 11x is going to be equal to 99. X is going to be equal to 11. Psych, x is equal to 9. All right, that's peachy, that's nice, but does this really solve what we were looking for? Nope. Well, we know that J to L is 120, that's given. But J to K, how could we solve for J to K? Well, J to K, they give us this nice little algebraic piece here. So if we plug in, we know that J to K is going to be 4 times 9 plus 6. So 4 times 9 is 36, plus 6 is 42. So we know that J to K is 42. When you're really quick with these, you can just assume that K to L is going to be the difference of 120 and 42, but I'll show the algebra for that. So you could say 7 times 9 plus 15, 63 and 15, 78. Done. I know this is all right because if I add J to K as 42 and K to L is 78, that will get me back to 120. And you know, maybe you're not convinced and you want to use a calculator. All right, sure. So 42, which was J to K, adding on 78, 120. 120, 120, we're good. Take this moment now, pause the video, try the next problem. You got that. So same song and dance, you know that T to V is 64. You know that T to U is 10x minus 1. U to V is 8x plus 11. So you could say 64 equals 18x minus 1 plus 11. It's going to be plus 10. So you're saying that 54 equals 18x. So what's that going to be? That's going to be x equals 3. All right, so T to U is going to be 29. If we plug in, 3 times 8 is going to be 24. 24 and 11 gets 35. And this all matches up to add and get 64. Great. TU, Temple University. That's where I went to school back in the 80s. All right, let's keep this moving. So we come across congruent segments. What is interesting about geometry is that we'll come across segments that look very similar, but we don't necessarily want to say that they're equal. So we will come across using congruent when we have numerical expressions with the same value. Yeah, in algebra we say that those are equal, but if we have two segments that have the same value, we say that the segments are congruent. So this little squiggly in the equal sign means congruent, meaning that they behave very similar, they look very similar, but they are not quite the same segment. They have the same measurement. So for example here, A to B is 1 inch. Let's assume that this is drawn to scale. C to D is also 1 inch. You could say that although these segment lengths are equal, these segments themselves are just congruent. So notice that they have equal distance, so the segment lengths are equal, but the segments themselves are congruent. So notice that there's a difference between length and just being equal. Identifying congruent segments, this is pretty easy. So we are doing what exactly? Using the diagram above, is AB congruent to DE? Great question. So we know that A to B is going from here to here. So if you want to use absolute value, this is from -2 to 3. So this is the absolute value of -5, so 5 units. C to D goes from 5 to 10. Absolute value of -5 is definitely 5. So yeah, AB is definitely congruent to CD. All right, well, that's what we can say. AB is congruent to CD. What about to DE? D to E is 4, so we would say no. And did they ask anything else about this? Yeah, this is just for extra. So if you wanted to, you could get practice on this, saying that A to C is going to be 7. B to D is also 7. But yeah, this is just extra, saying that A to C is congruent to C to B to D, yeah. But AB is definitely not congruent to DE, because 5 does not equal 4. AB was 5, DE was 4, so that's no good. All right, so let's take a break. We'll come back. We'll see more about midpoints and bisectors. That's a pretty easy section. Thanks for watching.